Fact 1, dark matter isn't there, but it is tightened. Here's the cleanest way to see the problem. Take a spiral galaxy. Stars far from the center should orbit more slowly, the way planets farther from the sun move slower. That's what Newton and Einstein predict when you tally up the visible mass. But when Vera Rubin and Kent Ford measured rotation curves in the 1970s, the speed stayed flat, too fast in the outskirts. It's like the galaxy's outskirts are gripping a hidden handle. The math says there's way more mass than we can see. Now switch lenses literally. Gravitational lensing lets us map mass by how it warps background light. In cluster after cluster, the strongest lensing happens where there isn't enough luminous matter to account for it. The showpiece, the bullet cluster 1E065756. Two clusters collided, gas slowed, but the lensing peaks tracked the galaxies, implying most of the mass barely interacts except via gravity. Something is there, not shining. Why this matters is simple. Our cosmology collapses without the missing mass. Structure in the early universe wouldn't grow into galaxies on time without a gravitational seed that doesn't pressure couple with radiation. Simulations with dark matter produce the web-like cosmic structure we actually observe. Take it out, and the universe looks wrong. But watch how we respond. We measure consequences and name a cause. So physicists tried to find the stuff. The classic pitch, WIMPs, weakly interacting massive particles born naturally in early universe thermodynamics. Build ultra-clean detectors underground, wait for a tiny recoil. Decades later, LuxZ-PLIN, Xeno NNT, PandaX, and others report null results that squeeze the parameter space. The WIMP miracle looks less miraculous. Okay, so maybe not WIMPs. Axions, ultralight particles that could solve the strong CP problem, and if they exist, act like a cold, diffuse fluid. Haloscopes ADMX and beyond tune microwave cavities through frequencies, listening for axions to convert into photons in a magnetic field. Hints, not yet. We push sensitivity, rule out ranges, keep going. Sterile neutrinos. They'd slip past the weak force and only show up gravitationally, tweaking X-ray lines and cosmology. Claims appear then fade. The chase continues. Meanwhile, some say the problem isn't new matter. It's old assumptions. Modified Newtonian dynamics, MOND, tweaks gravity at very low accelerations so galaxies rotate the way we see without extra mass. MOND fits many rotation curves with one acceleration scale, but struggles with clusters and cosmology unless you add patches. Relativistic MOND and other modified gravity frameworks try to match lensing and the CMB, but none is standard. Notice the pattern, negative space phenomena. Dark matter is defined by what it isn't, no light, no charge, no strong interactions, yet it rules motion on the largest scales. We're fitting the universe to our math and instruments, not the other way around. That's okay. Science often works that way, but it should lower our confidence in what solid means. Here's a detail people miss. In galaxies, dark matter seems to form halos with cores or cusps depending on the system, and baryons, normal matter, can heat and stir that halo through feedback from star formation. So even invisible matter is sculpted by the visible. The separation isn't clean, it's a relationship. In merging clusters, the dark component sails through, but in dwarf galaxies, small-scale structure hints at something warmer or self-interacting. That nudges models toward particles that talk to themselves weakly, changing halo shapes without lighting up. Remember the bullet cluster. There are messier systems like Able 520, the train wreck, and El Gordo where mapping is complex. One exhibit is powerful, population studies test the rule. So far, lensing surveys still demand extra mass while hinting at tensions. Matter clumping from weak lensing, S8, runs slightly lower than CMB inferred values. Either subtle systematics haunt our measurements, or the dark sector is richer than a single cold fluid. What's crazy is how comprehensive dark matter's fingerprints are. It stabilizes galaxy disks, anchors halos, sets up the scaffolding for gas to cool and form stars. Yet every direct search has come up empty. That puts us in an awkward spot. The universe behaves as if an invisible mass dominates, and our detectors insist they don't see it. When evidence and absence both stack up, you've hit a boundary. The deeper pattern emerges. We're repeatedly forced to accept invisible causes because the consequences are undeniable. In art, negative space defines the figure. In physics, these absences define the rules we trust. If mass can be invisible and still steer galaxies, check your confidence in everything that feels tangible. Speaking of invisible forces shaping everything you can see, the universe isn't just held together by a hidden mass. It's being pulled apart faster and faster. If mass raises questions, the acceleration raises alarms. If all this space is expanding, what's doing the pushing, and into what? Fact 2, dark energy breaks the map of the future. Okay, invisible mass holds things together. Now meet the invisible pressure tearing everything apart. In the late 1990s, two teams used Type Ia supernovae as standard candles, expecting to see expansion slowing under gravity. Instead, distant supernovae were dimmer than slowing predicts. The only way to square that, expansion is speeding up. Space itself acts like it has negative pressure. We call the driver dark energy. Again, that's a label, not a substance we've bottled. The cleanest summary lives in lambdictum, cold dark matter plus a cosmological constant lambda, a uniform energy density built into empty space. Plug lambda into Einstein's equations and you get accelerated expansion that fits supernovae, the CMB's geometry, and baryon acoustic oscillations. On paper, it's consistent. Under the hood, the numbers are absurd. Here's the mismatch that keeps theorists up at night. Quantum field theory says the vacuum isn't empty. It's a sum of zero-point energies of every field. Add them up with any reasonable cutoff and you overshoot the observed dark energy density by about 120 orders of magnitude. That's the cosmological constant problem. Right sign, wildly wrong size. You can fine-tune to cancel most of it, but at one part in 10^120. So 3 roads, none paved. 1. Vacuum energy really is a constant with a finely tuned tiny value. 2. It's not constant. Some dynamical field, call it quintessence, is rolling slowly, mimicking lambda today but changing over cosmic time. That gives you a time-varying equation of state parameter W slightly different from -1, which surveys are hunting by mapping millions of galaxies and supernovae. So far, W hugs -1 within current precision. 3. Maybe gravity itself is different on the largest scales. Modify Einstein instead of adding new stuff. F, R, gravity, scalar, tensor theories, massive gravity, brane worlds. These models tweak curvature's response to stress, energy to get acceleration without a pure lambda. But then you must pass solar system tests, binary pulsars, gravitational wave speed constraints, and cluster dynamics, while matching CMB anisotropies. Most candidates get cornered or require fine-tuning. Notice how the universe keeps rewarding stability with exceptions. Matter clumps. Dark matter made sure structure could form early. Dark energy does the opposite. The more it dominates, the faster everything dilutes away from everything else. Turn the clock forward and galaxies outside our local group disappear beyond any possible signal. The map of the future isn't just lonely. It's undefined by our usual guides because the ruler and clock are tied to a geometry being stretched faster and faster. Here's a subtlety. Acceleration is inferred by comparing distances and redshifts across time. Systematics matter. Are Type Ia supernovae truly standardizable across redshift, metallicity, dust? Surveys have tightened that. Distance ladders and H0 calibrations spark the Hubble tension. Local measurements versus early universe inferences don't match perfectly. Weak lensing's S8 comes in slightly low compared to lambdictum forecasts from the CMB. Either reductions are tricky, or the dark sector has more knobs than one constant and one particle. If dark energy is a field, where's its mass scale, couplings, and why hasn't it shown up in lab tests of fifth forces? Screening mechanisms try to hide it in high-density environments and reveal it cosmologically, chameleon, symmetron, Weinstein effects. But every success adds a moving part. If it's a true constant, why that value now? The coincidence problem. Why is dark energy density comparable to matter today, not overwhelmingly tiny in the past or utterly dominant long ago? Anthropic reasoning shrugs. In a multiverse of different lambdas, observers arise only where structure forms. That selects small lambda. Testable. Barely. Satisfying. Depends on your appetite for selection effects as explanations. What's crazy is how many independent rulers point to the same acceleration. Supernovae brightness, bow standard rulers, CMB angular diameter distances, galaxy clustering growth rates, even gravitational lensing statistics. You can swap techniques and telescopes. The pattern holds. It isn't a single instrument's bias, it's the sky-s. That's why institutions agree on the effect and disagree on the cause. The deeper pattern returns, fine-tuning everywhere. Dark matter saves structure formation, dark energy dissolves it. Two invisible hands, opposite directions, both tuned to matter-era scales. We keep replacing mechanisms with parameters and hoping the universe explains our choices later. So far, it hasn't. If space can accelerate by itself, then geometry isn't passive background. It's an actor with its own energy bookkeeping we don't understand. Push to smaller scales and the strangeness spikes. Because when you zoom in far enough, space doesn't just stretch, it stops behaving like space at all. Fact 3. Quantum entanglement violates your intuition about distance. Okay, space can stretch, but here, that's where between stops being useful. Einstein, Podolsky, and Rosen tried to corner quantum mechanics with a simple move. If measuring one particle instantly tells you something about a distant partner, then either influences travel faster than light, or the particles carried per-written answers, hidden variables. That's the EPR paradox. The idea was to show quantum theory incomplete without those hidden instructions. John Bell turned that philosophical jab into a test. He derived inequalities that any local hidden variable theory must satisfy. Then experimenters asked entangled particles the questions Bell prescribed. Choose measurement settings on each side, compare correlations, and see whether nature obeys the inequality. Decade by decade, the loopholes closed. Detection efficiency, locality separation, freedom of choice. In modern, space-like separated, loophole-free experiments, 2015 and after, the correlations violate Bell's bound. Local hidden variables are ruled out statistically. Why this matters is sharp. Relativity caps signaling at light speed. Quantum theory respects that entanglement can't send messages, yet the outcomes are more correlated than any local story allows. The spooky part isn't superluminal information. It's that the joint facts don't factor into parts with their own independent properties. Separate systems don't carry fully separate realities for those measured quantities. Watch what to look for. Entanglement swapping, entangle A, B, and CD, then a joint B. C measurement entangles a D, quantum teleportation. An unknown state reappears elsewhere using shared entanglement plus a 2-bit classical message. And device-independent cryptography, security certified from Bell violations without trusting device internals. These are working protocols. Notice how this collapses separate as a reliable idea. You can space stations a continent apart, time their choices to be random and near-simultaneous, and the statistics still demand a non-local structure. Not faster than light signals. No knob you turn here changes marginal probabilities there, but a deeper constraint linking outcomes as if the questions are asked on a single, distributed object. The pattern we keep hitting shows up again. Relationships first, properties second. Okay, but what about loopholes? Experimentalists anticipated that. They closed the locality loophole by ensuring the choice of measurement on one side can't causally influence the other within light cones. They closed the detection loophole by improving efficiency so you can't cherry-pick detected events. They improved randomness sources to protect against subtle correlations. Every time the tests got stricter, the violations persisted. If you want to keep local realism, you're pushed toward conspiracies, superdeterminism, where the universe pre-correlates measurement settings with hidden variables. That rescues locality at the price of undermining experimental independence. Maybe, but it's a steep cost. Here's what's crazy. Entanglement isn't rare or delicate in principle, it's the typical state of composite systems. In quantum many-body physics, entanglement patterns classify phases of matter. In quantum computing, entangled qubits are the resource for speedups. In condensed matter, topological order and error-correcting codes are entanglement architectures. The spooky is also engineering. Now connect this to earlier themes. Dark matter connected masses through gravity without light. Entanglement connects outcomes without signals. Invisible causes again, but now they're constraints on joint probabilities, not forces in space. It's a different kind of glue, one that doesn't push or pull, but restricts what can happen together. Remember this detail. In quantum field theory, locality means operators at space-like separation commute, no causal influence. Yet the vacuum itself is highly entangled across any boundary. That's why cutting space, say, tracing out a region, produces thermal-looking mixed states on the remainder. The thermodynamic flavor isn't an analogy. It falls out of tracing over entangled degrees of freedom. The boundary holds information about the bulk because of entanglement, a hint we'll need when spacetime itself starts to look emergent. This next one takes it further by breaking our comfort with order in time. In delayed choice entanglement swapping, you can decide to perform the joint measurement that entangles A and D after A and D were already detected. The correlations adjust as if the classification of what happened depends on a choice in the experiment's future light cone. There's no contradiction, no retrocausal signal. But the classical story, first events fix later outcomes, strains, and a geometric view of correlations starts to feel more natural than a chronological one. But wait until you see how we've weaponized this. Quantum teleportation moves states, not stuff. Quantum key distribution uses entanglement monogamy. If an eavesdropper shares entanglement with your pair's correlations weaken, and you catch it. Device independence means the very strength of Bell violation bounds the extractable randomness and secrecy. We're turning philosophical anxiety into certified resources. The pattern here is clean, a non-local structure underneath local appearances. The map is a network of constraints. The territory is what satisfies them. Space is a helpful coordinate system, but it isn't the whole story of what goes with what. If separation is questionable at the quantum level, what about the other absolute we lean on? A single, shared now. Entanglement already hints that slicing reality into independent parts is a choice, not a fact. Time is about to get the same treatment. Fact 4, time dilation says there is no single now. If entanglement messes with between, relativity messes with when. Start with the rule that actually works your phone. GPS only works because we correct the clocks. Satellites are higher up where gravity is weaker, so their clocks tick faster. They're also moving relative to you, so special relativity makes them tick slower. Add both effects, and if you didn't fix the rates, your maps would drift by kilometers per day. That's not philosophy. That's a Patch Tuesday for reality. Why this matters: simultaneity isn't universal. What counts as now for you is now for me if we're moving differently or sitting in different gravitational wells. Einstein's point was time is an illusion. It was tighter. Time is a dimension stitched to space, and motion bends how you slice it. You live in a sequence of space, time events, your world line. Another observer slices that four-dimensional loaf at a different angle. Their present cuts a different set of events than yours. No single global now survives that geometry. Watch for 3 anchors. First, the twin paradox. One twin stays on Earth, the other accelerates, cruises near light speed, then returns. On reunion, the traveler is younger. There's no contradiction because the world lines aren't symmetrical. Acceleration breaks the mirror and carves unequal lengths of proper time, the time measured along each path by each twin's own clock. Second, gravitational time dilation. Clocks tick slower deeper in a gravitational field. Put one on a mountain and one at sea level, they diverge. We've measured that with atomic clocks, planes, even lab-scale height changes. Third, black hole horizons. As you hover closer to a horizon, time stretches so severely relative to faraway observers that your processes slow to a crawl in their coordinates. To you, your own time feels normal. That mismatch is the point. Here's the geometry payoff. In relativity, causality is literally a shape, the light cone at each event. Anything inside your future light cone can be influenced by you. Anything outside can't be, regardless of how you boost your rocket. Causality becomes a map constraint, not a metaphysical rule. That's why we keep saying causality is geometry. The order of before and after for space-like separated events can flip depending on who's moving. If your now can't be everyone's, then what exists right now becomes observer-dependent too. Notice the pattern meeting entanglement halfway. We already saw that the vacuum's entanglement makes subsystems look thermal when you trace out the rest. In curved space or accelerated frames, that becomes the Unruh hint. Accelerate hard enough and the vacuum looks like a warm bath. Whether particles are there depends on your motion. Measurements aren't passive. They define which slice you're calling real. Okay, but does this wreck cause and effect? No. The prohibitions stay intact. No signal outruns light and local dynamics stay consistent. What dissolves is the idea of one cosmic clock. Even everyday tech betrays this. Fiber networks and stock exchanges synchronize clocks with relativity corrections or lose money. Your wristwatch is parochial. The universe doesn't endorse it. Remember this detail that feels small but isn't. In general relativity, mass and energy tell spacetime how to curve, and curvature tells matter how to move. Clocks aren't innocent bystanders. They're part of the geometry. That's why GPS works only when you solve Einstein's equations well enough to correct the orbits and the rates. The present in those systems is a convention chosen to keep the network coherent, not a discovery of a universal slice. Now push to extremes. Near a black hole, tidal gravity can stretch time so dramatically that infall looks frozen to a distant observer, while the infaller experiences a quick, finite plunge. If you film both stories and compare later, they don't stitch into a single shared now. You reconcile them by respecting the cones. That's also why horizons trap information flow. For an outside observer, signals redshift and fade. For the infaller, they scream by. Same physics, 2 slices. What's crazy is how much this reframes everyday statements. At the same time, across the galaxy is a choice of coordinates, not a fact. If you want a clean now, you pick a slicing, say, one that follows the average cosmic rest frame defined by the microwave background. It's useful but not sacred. Change the slicing and stories reorder without breaking causality. The deeper pattern is back. Observer dependence isn't a glitch, it's structural. Non-local ties in quantum theory made separate unreliable. Relativity makes simultaneous unreliable. Your present isn't mine, and neither of us is wrong. We live in slices of a four-dimensional constraint network, and what we call cause is the path we trace through it. So if time bends and now is negotiable, why does experience still flow one way, from remembered past to felt present to open future? The equations don't care. That arrow is coming from somewhere else. Fact 5, the arrow of time shouldn't exist, but it does. Here's the tension. The microscopic laws, the equations for particles and fields, run just as well backward as forward. Flip the velocities, change t to minus t, the math doesn't flinch. But your coffee cools, never heats itself. Eggs shatter, never unshatter. Memories point one way. Where did that direction come from if the rules don't care? The standard answer is entropy, the number of micro-configurations that look the same at our coarse, macroscopic level. High entropy means more ways to be arranged. Low entropy means fewer. Systems wander from rare, ordered states toward common, disordered ones simply because there are vastly more ways to be messy. That's the second law, but look closely. Nothing in fundamental dynamics forces that trend. The trend appears if you start from low entropy. So the real puzzle moves back a step. Why was the early universe in such a special low entropy state? The microwave background is astonishingly uniform to 1 part in 100,000. Gravity makes the story weirder. For gases, uniformity is high entropy. For gravity, uniformity is low entropy because clumping, forming stars, black holes, opens far more microstates. That means the smooth beginning was extraordinarily ordered by gravitational standards. We've been rolling downhill ever since. Watch for the tools people use to probe this. Fluctuation theorems quantify how often small systems momentarily buck the second law. Entropy can go down briefly, but the odds scale exponentially against big, long-lived decreases. Boltzmann's brain is a thought experiment that pushes the logic to absurdity. If you wait long enough in an eternal thermal bath, random fluctuations will occasionally assemble a self-aware brain with false memories. That's a reductio. If your cosmology predicts that typical observers are fluctuation brains, you've built a world that explains away experience rather than grounding it. Inflation often shows up as a patch. A scalar field rolls slowly and exponentially irons out curvature, defects, and inhomogeneities. Quantum fluctuations seed structure after inflation ends. It's powerful, but not a free pass. You still have to ask why the inflaton started in the right place with the right properties, and whether inflation sets initial conditions or reframes them. The low entropy question sneaks back in. Notice the pattern we keep using. We explain the arrow with a boundary condition, not a dynamical law. We say, given an extremely special past, typical evolution goes toward higher entropy. That's true. But why that past? One move is the past hypothesis. Stipulate that the universe began in a very low entropy macrostate. Full stop. It's clean, but it's a label on the mystery, not a mechanism. Here's an angle that links to quantum theory. When you ignore degrees of freedom, trace out the environment, subsystems look mixed, often thermal. Entanglement growth in an isolated quantum system makes local observers see entropy rise even when the global state evolves unitarily and time-symmetrically. The arrow shows up when you choose a tensor product cut and a coarse graining. That sounds like a cop-out until you notice it mirrors how we live. We're local, finite, and constantly discarding information into the environment. Now fold in black holes. Toss in a bookshelf's worth of ordered stuff. The horizon area increases, encoding a staggering entropy. Hawking's calculation says the whole radiates thermally and evaporates. Where did the information go? If it's lost, quantum evolution isn't unitary. If it's preserved, it must be smeared in correlations across the radiation in a way no simple thermometer sees. The modern take favors preservation. Page curves, island formulas, and holographic calculations suggest unitary evaporation with subtle entanglement patterns. Either way, the arrow is loud. Horizons hide, areas grow, thermal spectra dominate. It screams one way even as the fine-grained bookkeeping stays reversible. Here's the detail people miss. The arrow you feel isn't just thermodynamic, it's psychological and computational. Brains are low entropy, out-of-equilibrium organs burning energy to form stable memories. Writing to memory increases entropy in the environment. You remember the lower entropy past because the records were created then. That's not circular, it's a constraint. Reliable records require free energy and dissipation. Your sense of flow is the byproduct of error-corrected snapshots laid down by irreversible processes. What about reversing the movie? In principle, you could arrange an astronomically precise state that unmixes the cream. Practically never. Any noise ruins the path. The second law is about overwhelming odds, not logical necessity. Maxwell's demon failed once Landor showed erasing memory costs energy and increases entropy. Clever bookkeeping doesn't beat statistics. Pull back to the cosmos. Two arrows dominate your fate. Dark energy stretches space, thinning matter and isolating islands of structure. Entropy climbs as stars burn, planets cool, black holes gulp and glow. Given enough time, protons may decay, black holes evaporate, and only thin radiation remains. That's the quiet end. A cold, dilute universe where almost nothing happens because almost everything already has. So the equations don't care about direction, but the world we inhabit clearly does. The fix isn't new dynamics. It's recognizing that arrows come from improbable beginnings plus typical evolution plus relentless coarse graining. We keep outsourcing the improbability to the past, and we still can't look back far enough to check.